Hi folks, and welcome to the Heart of the Matter. In this lecture, what I'm going to cover is the ECG, the autorhythmic cells, how they function, and Wigger's diagram. So the other reviews of the heart were going to be on external videos, and you can look at that or some of the readings on OpenStax. So let's go to this, the electrocardiogram, the ECG or the EKG as it is said in German. And what is this? So this is a measurement of electrical current. And this electrical current has been generated by cells that are autorhythmic cells, action potentials from the heart itself. Okay, and we're going to be able to measure that. So it's a measurement of electrical activity. Now, the mechanical events, you're not seeing that. You're just seeing what's happening electrically. There's these waves, these spurts of electricity, of current. And you assume that if they're working correctly, then what's going to happen is the contraction is going to be perfect. But it's an assumption because what you're looking at an ECG is just electrical waves, just electrical events. So it's going to measure the sum of all electrical activity in the heart, the entire heart, not a recording of one particular cell like we've done before, right? Oh, this is a recording of what happens. It depolarizes and it repolarizes. It's not that. It's what is happening in this entire organ. So it's not a direct recording of an action, one action potential. Depolarize, repolarize. No, it's what's this wave if I measured this wave of electrical activity. It's measuring differences in potential before and after. And depolarization and repolarization are both seen as uphill curves. So remember, we're measuring blips that happen in the heart as electrical activity goes and comes. And both of them are going to be blips. It's not, oh, if it depolarizes, it goes up. If it repolarizes, it goes down. They're all going to be up. Okay? Kind of have to get your mind around that one. So there are three waves of an ECG, the P wave, the QRS complex, and the T wave. And this is a recording of one, and we've enlarged, and let's just focus on one here. So the first, the P wave, is a blip that goes up, right? An upward blip. And that is atrial depolarization. So it's going to begin, those autorhythmic cells are in the atria. It's going to begin in the upper part of the heart, and then you're going to see a blip just there, just in that section. The QRS complex is ventricular depolarization. Now I'm going to depolarize the atria, now I'm going to depolarize the ventricle. And the last one is putting it back the way it was, which is repolarization of that ventricle. But let me show you in pieces, okay? As a definition, waves are not blips. I call them blips. They're actually waves. They appear as deflections above or below the baseline, and segments or sections of the baseline between two waves. So here is an ST segment. This is a particularly important one to look at during heart attacks. This is where a cardiologist can look, and see if there's been cell death in the heart and that line doesn't look flat. Okay, let's start right from the beginning. So if we had the initial depolarization of the atria starting, it's only happening up here in the purple region, then you're going to have a piece of a P wave, correct? Now let it run, and what's going to happen is the entire atria are now depolarized, and so the P wave has been completed, right? So all of that's depolarized, and now these diagrams are really nice because they show the outcome, the mechanical outcome. It's like, oh, now the atria are going to contract because they've received that signal, that electrical signal. But remember, what you're looking at is just a signal. This is nice to have there so that in your brain you know, all right, depolarized contractions happen. Next, then, this electrical activity in purple would start coming down the center here, the septum, and you would see the little beginning of a Q. You let it run, and it's now spreading to the walls of the ventricles. You see an R. It's now come down. A lot of it is depolarized. So you're seeing now coming down to the S. It's nice to have it in stages. And as it's completed, the entire ventricle has been depolarized. The QRS is finished. What's going to happen mechanically? The ventricles are contracting, but they started contracting right after the Q about, okay? And it's going to last this long because this axis here is time. So that's good. Now, repolarization is indicated here in red. So this is still depolarized, but I've already begun some of that repolarization, and that is not going to be, remember, it's not going to be a dip. It's also going to be, again, a curve, because it's showing that there's been a change. It doesn't matter what it is. It's a change. And so that repolarization of the ventricle is going to be the T wave. Okay, so big reminder, P represents depolarization of the atria. QRS represents depolarization of the ventricle. T represents repolarization of the ventricle. And where is the repolarization of the atria? It's hidden. It's hidden. It happens somewhere around here. But because this was such an overwhelming curve here, we didn't see a separate one. We don't see 4, we just see the 3. And those are the electrical events of the cardiac cycle. And now notice nothing's happening, nothing's happening, nothing's happening until we begin a new cycle. And that is the end of that. But we're going to continue on here and take a quick look at autorhythmic cells. So autorhythmic cells are these fantastic 1% of the cells of the entire heart that have this incredible, I'm tripping up over my words today, incredible capacity of creating an action potential spontaneously. They don't have to wait for the brain to send that signal. They will just do it. So once they create that electrical event, it can spread, remember, from cell to cell through gap junctions over to all the other contractile cells. But it's the electrical ones that are sending the signal and the others are receiving. So those are the autorhythmic cells, pacemaker cells of the heart. So as a reminder, most of them are not those. Most of them are contractile cells. That's what they do really well. They contract. They can contract super well. 99% of the cells in the heart are myocardial contractile cells. But the other 1%, which we're talking about now, are then the autorhythmic pacemaker cells, and they are going to keep that rhythm of firing through the heart. Where are they? The location then is very specific, and we have a node, which means a bunch of them, in the right atrium. And that electrical activity is going to radiate through this atrium and over to the other one, right? Over to the other side. So both atria now connected. But it's not strong enough to actually go the whole way down into the ventricle. So that depolarization hits yet another node. Node means a group, a bunch of those cells that is situated here. In the base, is sort of the base of the atria, beginning of the ventricle. And that is going to be sufficient to radiate all the way down the septum and up the sides. Okay, so this is SA node, goes to AV node, AV, atrioventricular node, and then there are very specific names for the sections of these cells as they kind of play tag. And tag you, tag, 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 and they go radiating. So that first section of tag there is the atrioventricular bundle, which is a stem here, until it divides to 2 separate ones, as one's going to go to the right and one's going to the left. And those are bundle branches. And they branch down to the bottom and then are going to make their way up the sides of the ventricle. And those are the Purkinje fibers. Okay, so that's the sequence that this tag team plays, radiating this electrical activity through the heart. What do they look like? Why are they so different from the others that are contractile? Well, they're smaller. They contain a few contractile fibers. They're actually able to contract, but that's not what their main function in life is, right? They look tinier. It's good to know that the SA node is the speediest. It's 70 to 80 beats per minute is the rhythm that it's going to establish of delivering these action potentials. The AV node delivers at 50 if it were to have to act on its own. Usually it just follows the leader and it'll just fit into the 70 to 80. But if you were to damage the SA node and remove it, then the AV node would take over at a slower pace. Is that clear? It's going to do it. Each one has a different velocity if they were to have to follow the leader. So the Purkinje fibers are quite slow if they're not following leader SA node. Okay, so that we have seen that in damage to the SA node, and then the AV node is able to take over. A defibrillator that you've probably seen at the gym or airport or somewhere is because if these different nodes decide to fire independently and they decide to all begin their contraction, what's going to happen? All at different velocities. Then the heart doesn't know what to do because these signals are coming from too many places at different paces. So the heart starts to fibrillate, which is try and respond to all of them, and it doesn't have the rhythm that it has to have of depolarization. So the defibrillator, what it does is sort of gives it a larger shock that overrides all these different little signals, and then it tends to go back into pace again. Also, the AP, the action potential in autorhythmic cells, is really not the same as skeletal muscle. It's called a pacemaker potential, and as it's not receiving a signal from a neuron, it actually looks different if you were to record it. And this is what it looks like. So do you remember how the other one looks, right? It just went shot up and down and overshot. In the cardiac autorhythmic cells, it starts at about -60. And it takes a long time to just sort of slowly, long time, 300 milliseconds, but that is long. It's not 2 milliseconds like it was for the skeletal muscle. It's a slow depolarization to threshold, and then it fires and then comes back down again. And then a slow depolarization to threshold, and then it fires and does its thing again. So the sodium and potassium channels are opening just like the action potential reaching a skeletal muscle. But because this is autorhythmic, because it's doing it on its own and it's not getting a signal, it's going to have to create it by itself. And it does so by using also calcium channels, but leaky sodium channels. And slowly this becomes more positive and more positive and more positive, and then it fires. So we're not going to go into a lot of detail on that. If you'd like to see more on that, your text has that. But just for now, I think what you need to remember is action potentials in cardiac autorhythmic cells are sort of different. They're different from the action potential of one cell that you could record of a cell in skeletal muscle, for example. What I want to show you next is Wigger's diagram. I'm going to leave that for the next video. It's a little confusing, so I want to give myself more time. So that's the next video. See you in a bit.